Hello, my name is Daniel Bautista, and I'm going to present our work entitled Bringing Light to the Insertion of Cochlear Implants using Tetrapolar Bioimpedance Measurements. Our research is based on cochlear implants. These are the most effective treatment for sensorineural hearing loss. One of its most critical components is a very tiny electrode array which is placed in the scala tympani, one of the helical chambers of the cochlea that we can find in the inner ear. The implantation of this electrode array is very challenging, as we can observe in the picture on the left, where the electrode array is being inserted through a very tiny hole, more or less the same dimensions of the electrode array. One of the big problems of the implantation is that the surgeon cannot see further than the insertion point. This lack of visual feedback in a highly sensitive anatomical structure like the cochlea leads to problems such as touching sensitive structures, misjudging insertion angles, or position the electrode array at the wrong place, even translocating the implant into a neighboring chamber. As a result of all these problems, we can generate what we call intracochlear trauma. And intracochlear trauma does not allow for residual hearing preservation, which is very important to provide the patient with better hearing outcomes. In this work, we want to tackle the problem of lack of visual feedback. For this, we intend to provide the surgeon with a tool that allows him to estimate the orientation of the implant within the cochlea during insertion using tetrapolar bioimpedance measurements. To test the feasibility of our hypothesis, our approach consists on a finite element method model with a cochlea and an electrode array that has 4 electrodes inserted in this cochlea. The cochlea model used is a simplification of the much sophisticated inner ear anatomy. We consider 3 main fluidic chambers: scala tympani, scala vestibuli, and the basilar membrane in between them. The 3 chambers are surrounded by bone. An image of the 3D model can be seen in the top middle picture, and a cross-section in the right picture. The electrode array can also be observed in these 2 pictures, with 2 of its electrodes being used for electrical impedance measurements. This electrode array consists on a silicon carrier which is 18 mm long, 0.5 mm in diameter, and has 18 platinum electrodes. For our simulations, we use COMSOL multiphysics, and in the bottom middle picture we are showing a schematic of the model used. We check reciprocity to assess the validity of our simulation model, and we simulate a spectroscopy impedance measurement at different frequencies. As it can be seen in the picture on the left, in our simulation we consider an angle of 0 degrees when the implant is facing the inner wall, and we count angles clockwise. Our results can be seen in the picture on the right. These results show that the impedance magnitude changes significantly as the electrode array orientation within the cochlea changes. We can also notice how these changes become more obvious as we increase the frequency of the simulated current source. In summary, our results allow us to affirm that impedance measurements can be used as a sensor to estimate orientation during cochlear implant surgery. In future, we plan to extend our work
and study if we can observe changes in impedance for different positions. Also, we want to study how the electrode topology and shape affect the electrode array sensitivity and in turn their effect on estimating the electrode array position and orientation. And finally, we want to conduct experiments to validate these findings. So this was all for our presentation, and thank you for listening.